then we can start. So for those who may be joining us for the I am Dr. James Katende from the Department of Mathematics at the University of Nairobi, and we do this training every 2 weeks where some mathematics as well as some questions that are likely in the Capet Kenya Mathematical Olympiad, which is a high school maths contest that is open to all high school students who are eligible. So today we shall be talking about the Pigeonhole Principle. If you have any questions, always you can feel free to just put on your mic and ask the questions. Because I don't have someone to follow up on the chat, so it's I may not be able to monitor the chat, but for the any questions you have, you can just put on your microphone and ask. So let's look at this statement of the Pigeonhole Principle first. So the first statement is this: if we have m plus 1 pigeons and m pigeonholes, so we want to place this m plus 1 pigeons in m pigeonholes, where m is a positive integer, then there must be at least one pigeonhole that will have more than one pigeon. So to illustrate this, I think I can try to use a small example. Suppose we have 3 pigeonholes and we have 4 pigeons. So if I have the 4 pigeons, I can try to spread them out through the boxes. So after I've spread out the first 3, I still have one extra pigeon, and I only have 3 boxes. So that extra pigeon must go into one of these boxes. So then you'll end up with this box having at least 2. So one of the boxes have more than one, at least. If you have m plus 1 and m pigeonholes, this is always possible. The next one says, again, it's basically a restatement of the same, but in a slightly more general. So this one says if you have m plus 1 pigeons and you have n pigeonholes, then there must be at least one hole with at least number of pigeons. So this is a floor function. Floor function simply means this: if the floor function of a number like 4.2 would simply give me the largest integer that is smaller than 4.2. So the floor of 4.2 is 4, or the floor of 7.9 would be 7, and so on. So that's what it means. So if we have these two numbers, we have the number of pigeons and the number of pigeonholes, then if we are to place the pigeons in the pigeonholes, you will end up with this, at least one, with one hole having at least this number of pigeonholes. Okay. Then there's one more statement, which is if you have infinitely many, you partition these infinite number sets, then there must be at least one set containing infinitely many elements. We may not use this third one, but it's just a, if you have infinitely many elements, you divide a set into a lot of subsets, then there must be at least one of the subsets that will contain infinitely many elements. So we'll focus on two. We'll be when solving this problem, what you It may not always be easy to identify the pigeons and the pigeonholes. Sometimes you may need some manipulation to be able to identify them. And then after you've identified them, then you can apply these two ideas. Sometimes you may need to restructure the problem into a form that can be into form where you can apply this. So the next thing now is to look at some problems. Now there are proofs for all this. I have avoided the proofs, but I suppose the statements are reasonably clear. If you have any questions, you can ask. In the interest of time, and also some of the proofs are beyond the scope of for some students. I think I left them out. But we don't need the proofs. We need to be able to apply the two statements. That will be our focus. So I will go to the first question. So this first question says we have a bag that contains 200 marbles. We have 60 red ones, 60 blue ones, and 60 green ones. And the rest, the remaining 20, is a mix of yellow and white. So out of these 20, we don't know how many are yellow and white, but in total, the yellow and white will be 20. The question asks, if the marbles are chosen from the bag without looking, what is the smallest number of marbles one must pick to guarantee that among the chosen ones, there's at least 20 of the same color? So that's the first question. So we need to figure out what's the smallest number we can pick, so that among the ones we have picked, we are sure there's at least 20 of the same color. I could let you read the question a little before we move to the solution, so that you can pick up the important data from the question. So I believe you have time to read. So, but if you need me to move back to the question, I can always move back to the question. For now, I will go to the solution. Oh, there's a part of the solution that has been cut out. I will explain it. So we have this is a problem we have. Let's see in what way can we make sure that we come close to picking 20, but we don't pick 20. So the first is by getting 19 of red, 19 of blue, and 19 of green. And then you pick all the 20, yellow and white. So that gives you a total of 77. So if you pick 77, you cannot guarantee that there will be at least 20 of the same color, because you have found a configuration where there are not 20 of the same color. So your answer must be more than 77, right? So the next thing you will try to do is to increase this 77 until you get to some number that makes sense. And since you just need one more to cross the line to get to 20 from the numbers that you have picked for the red, blue, and green, you can try to increase this by 1. So now suppose you pick 78. Among the 78, the yellow and white ones, of course, will be at most 20. And when you do that, you're left with 58, right? So out of these 58, we need to put them into 3 pigeonholes. We have things that we need to put in. One of the pigeonholes is red. They will plus one pigeons in one of those pigeonholes, right? So let's see if this 20 for these 58 that are remaining. So if you take m plus 1 to be 58, then m will be 57. So what you're looking for is, the number you're looking for would be 57. Oh, my writing has gone wrong there. You'll be looking for 57, the flow of 57, which is now m. Remember, m plus 1 is 58. And you divide this by 3. Pigeon is 3, then plus 1. So we are guaranteed that at least one of these 3 pigeonholes will have 20, right? If you are to split into 3. So 57 over 3 is what? Is it 19? And 19 plus 1 will be 20. So if you pick 78, then you're guaranteed that at least there'll be 20. There'll be at least 20 of the same color. So there can be more actually under this configuration. You can pick more than 20 of the same color, but you're guaranteed that there'll be at least 20 of the same color in one of the boxes. That question, I don't know if anyone has a question or comment. Is it making sense? Okay, I will fix these slides, but the part that is missing, I have explained it by writing. Okay, so we will move now to the next question, if this is clear. So the answer is 78. You need to pick a minimum of 78 to guarantee that there are at least 20 of the same color. Evans, you have a hand?
Yes.
You have a question?
Hello, sir.
Yes.
How did you?
Yes, I can hear you.
How did you come up with that 77 maples?
Okay, we want to guarantee that there are at least 20.
Yes.
Ones. Okay. So I want to look for the smallest number. The smallest number that not see 20, right?
Yes.
Of the same color. Now, if I want to, and the smallest would mean I have 19 of red, 19 of
yes,
blue, 19 of green, and all the yellow and white.
Yes.
Yeah. So you pick all the yellow and white, then you can get to 20. The others that can get to, because the red are 60, each of them one, but the yellow and white can never get to 20. So you just pick all of them anyway.
Yes.
To make sure that you don't interfere with the others.
Okay, sawa.
So now, if you pick 77,
yes,
we're on the same page now. Your question is fully answered?
Yes.
Okay. So I can move on to the next question. So the next question says, if 51 numbers are arbitrarily taken out from the first 100 natural numbers, prove that there must be 2 of the numbers drawn such that one is a multiple of the other. So the question says, if you pick 51 numbers, if you're 100 numbers, these natural numbers from 1 up to 100, if you pick exactly 51, then out of the 51, there must be two numbers drawn such that one of the numbers will be a multiple of the other. So we just need to find. So again, I'll let you read the question for a minute or so, then I can move to the solution so that you can capture all the data you need. So again, if you look at this question, it's not obvious that you should be using the pigeonhole principle, but you can restructure it and rephrase it in a manner to apply the pigeonhole principle. So we will see that in the solution in a minute. So we are going to make use of the following property, that any integer that you pick can always be written as a power of 2 multiplied by an odd number. So for instance, if I have say 5, if the number itself is odd, I can write it as where s is allowed to be 0 multiplied by 5, because 2 raised to 0 is 5. This is always if I put it as 2, 3. If I have an even number like 20, I cannot write it as 2 squared, 2 squared 5, right? Any number you pick between as an integer, it is always possible, a positive integer, it's always possible to write it in this form as 2 raised to some power multiplied by an odd number. Okay. We'll move from the board. There are exactly 50 odd numbers. If you look at the numbers from 1 to 100, we have exactly 50 odd numbers, right? So the distinct value of Qs, the Qs that you can get are 50 in total. So for each of those Qs, you can have a class of numbers written in this form. Total of 50 classes. So for each odd number, we end up with a class of integers written in this form. So for instance, if Q is 7, you can collect all the possible integers where Q is equal to 7, and this is your list. And for each odd integer, you'll be able to not having in common, right? So once you pick all these, the list will not have anything in common. So we maybe just to add one more example, if Q is equal to say 9, you start with 9 itself in the list, then 2 times 9 will be 18. So you keep going on. Then 2 squared times 9 would be 36, and so on, until you exhaust all the numbers that are in this form with 9 as Q. So each odd number will give you a class like this, right? The odd numbers more than 50, now we'll just have one element in the class, because if you multiply them by 2, you get another half, right? But you end up with 50 of these classes containing all the numbers that are written in this form and containing all the numbers from 1 to 100. So what it means now is you have 50 pigeonholes, right? And orange pigeonhole are multiples of, at least one is a multiple of the other. So for instance, if you look at this pigeonhole where Q is 9, you can see 18 is a multiple of 9. So you'll find at least two numbers in there where one is a multiple of the others in each pigeonhole. So now if you pick 51 numbers, you'd have to exhaust all the odd numbers, right? So we have Q, maybe Q1 up to Q50, right? Pick 51 numbers out of all the 100. Out of these 50 boxes, you can place them in the following fashion. You place the first number that you pick here, second number here, until you reach the 50th number rather. And you still have which must fit into one of these blocks again. So the 51st number fits here. So it will have to fit in one of these boxes. And any two that you pick from this box, any pair that you pick from this box, one must be a multiple of the other because of how we constructed the box. So that's the strategy behind the solution. So I hope this makes sense. Any questions on this? So the pigeonhole were the sets that we created. And these sets contained 100 numbers that we need. But inside sets, we know there are at least two that if you get two, one will be a multiple of the other because of the way they are set up. Right? And so for that reason, what do I want to say? For that reason, if you take this as a pigeonhole and you're picking 51 numbers, you can spread them out until you get the 50th. Then the last number must be picked again from one of the remaining. So that means you must pick one of the pigeonholes. Now the pair that you pick will guarantee that one of them is a multiple of the other because of the way the contents of a pigeonhole have been selected. Okay. Okay, so let me proceed. If you need us to go back to the solution, if you have any questions, please feel free to say so. We can always go back. So the third question says the following. So this one says that if you have a set containing n positive integers, there must be a subset of this set such that the sum of all the numbers is divisible by n. The claim is that out of these four, you should be able to find a subset whose sum is divisible by 4. So this will be 3, a set containing the n integers just giving an executive, you just need n positive integers, but this will serve the purpose to illustrate the point. So it's it plus 2 by 4. So what it says is that if I have any of integers, a1, a2, and this will go all the way up to an, and it's possible to find a smaller selection of numbers in here such that they are sum n. And these are just in there. They don't have to be consecutive. So I hope that explains the question. We'll move to the solution. So what I put there on so what we look at is the general set. To create a new set of, just takes the first value. B2 will be the sum of the first and the second. B3 will be the sum of the first, second, and the third, and so on. And then the last one, Bn, will be the sum of all the n numbers. Okay. So because these are all positive numbers, B1, B2, all the way up to Bn are distinct numbers. They are all different. Equal. So for this one cannot be equal to B2. It's not possible because I have added A2 to A1 to get B2, and A2 is a positive, so not equal to B2. In fact, this is a strictly increasing sequence of numbers. What I mean by that is that B1 is strictly less than B2, so they can't be equal, and this goes on to the end. Everything follows that. It's a strictly sequence like that. So we have established that all so this gives you the sums. So we are looking for a situation where at least one of these sums, because these are sums of a subset of the elements in here, we want at least one of them to be divisible by n. So if some of the if one of this you don't worry about, but none of it, let me just complete clarification. So what if any of these numbers in here are divisible by n, then all you need to add is two of the numbers which are divisible by n. So for instance, if B1 and B3 are divisible by n, if I add them, I get a new number which is divisible by n. So in that case, my work is done. I don't need case these numbers to work to be n are divisible by n. That is not true. Be mute the noise. We'll continue just. Okay, so clear. If n guaranteed to number B1 up to Bn is divisible by n, we still get a subset as a multiple of. So if none of them are divisible by n, then their remainders when by n are all 0. Now, anytime you divide a number by the largest possible remainder you can get is n minus 1, right? I'm trying to get the, oh yeah, sorry. We'll go to click on the draw thing. Now, if none of them are divisible by n, it means, for instance, if I have a number like, it's not, it means it will be some multiple. So, some multiple of n remain R1. So if B2 is also not divisible by, I can write it as a multiple of, so maybe I call this one K2 multiplied by n plus some remainder, a non-zero remainder. It has to be a non-zero remainder because none of them are divisible by. So this is all the way up to the last one. Bn will be equal to of those, but the total number of possible remainders becomes our pigeonholes. We have only n minus 1 of those, right? N remainders, I need to put them in n ones, right? Or rather, I need to pull them out of these n minus 1 possibilities. So it means I must repeat one of them. So at least two of these remainders will be equal. Is that making sense? I've muted. It has worked. Okay, I think the noise is gone now. So like I said, we have a total of n possible total remaining will be n plus 1. For instance, if I'm dividing the total number of non-zero remainders are either one, the only remainder get be either 1 or 2. 0. That's only two possible remainders. So if I have three numbers from this set, I have to repeat at least one of them. To get a number, I have to repeat either or a 1. So it's the same situation here. I have a total of n minus 1 possible non-zero remainders, and I have all these n remainders here that are computed, and they can't exceed n minus 1. So at least two of these must be equal, right? So if they're equal, so suppose they're equal for let's see, let me just go on to the next page. Use exactly. So suppose we pick these two to be BI. If these are the two numbers with the same remainder, where I and then we have the following situation. If you get the difference, then the difference will be the difference first of all will be non-zero, and it will be, but that difference is actually some. So we have guaranteed that we can always find a subset of the original set whose sum will be divisible by n. Is that making sense? Are we together? Okay, so is there something I need to repeat, or some section that did not make sense? At least I need to know if at least one person understood. Or there's someone here who was saying, could we go back to question 2? Okay, I will go back. Now, one thing, I'm not able to follow the chat when I'm doing the presentation. So please, if you need to ask a question or make a comment, I propose that you just put on your microphone, you ask a question, and then you can always put it off after you have made your comment or asked the question. So should I repeat the solution, go through the solution again, or it has made sense? So to make this part look clear, so for instance, suppose J is suppose I pick, sorry, the one we'll go back in a minute. So suppose by chance one to one and say B4, right? But B1 is just A1, and B4 will be equal to A1 plus A2 all the way up to A4. A3, that's how we had set up these values of B. So if these were the ones that are equal, if B1 is the one that's equal to B4, or rather their remainders, if their remainders are the ones that are equal, then their difference will be divisible by n. Why is it different? Because if it's supposed to be some multiple, so it's a multiple of n plus equal 1. Now we have established that B1 and B4, or rather for sake of, without loss of generality, let's assume that the ones with the, if they're the ones with the same remainder, then the difference, B4 minus B1, so B4 is known here, B4 is A1 all the way up to A4, the sum, and B1 just is A1. So B4 minus B1 will give me A2 plus A3 plus A4. Now this number is definitely divisible by 1, but by n, because if you subtract this, B4 minus B1, you will end up with Sn minus Tn. This is actually equal to Sn minus Tn. So technically what you end up with S minus T. So you end up with a multiple of n. So it's divisible by n. If the two remainders are equal, this difference will be a multiple of n. But that difference is a sum of a subset of some elements of the original subset. So we have found a subset. The subset we have in this case would be A2, A3, and A4. And the sum of the elements in that subset will be divisible by n. Are we, does that shed some light?
Excuse me, Dr. James Katende.
Yes.
So for us who came in a bit late, we are a bit lost on the Pigeonhole Principle and what it is about. I'm finding it very difficult to internalize the concepts.
Yes.
Because I don't understand what the principle is supposed to help with. or to solve?
I don't know how much time we have. We have about 10 minutes. There are two ways we can do this. I will share the recording, or we can go back and quickly explain the pigeonhole principle before we come back. So essentially, I'll just explain it for this question, but I will share the recording. It's best if you move out of the presentation with something concrete instead of being completely lost. So I will repeat this. So the version of the pigeonhole principle that you're using for this question is the following. If I have m+1 objects, right? And then I have, so these are my objects, or the pigeons, the ones we call pigeons. So I have m+1 pigeons, and I have m pigeonholes, or if you like, boxes. So I think boxes is faster to write, so I will write boxes. Usually the boxes are what we call the pigeonholes. So if I distribute these m+1 pigeons in these m boxes, I am guaranteed that there will be at least one box with 2 pigeons. Does that make sense?
It does.
Was it Bill who was asking?
Yes,
But
it
keep
was
this in
me.
mind. Anytime. Yes, yes. Okay, so I will repeat the solution. Now, if m+1 pigeons are distributed into m boxes, then there must be at least one box that has 2 pigeons, right? So that is guaranteed. I think you can see the logic behind that, because if I want to avoid the situation where there are at least 2, I will try to spread them out as much as possible up to the mth one, but I will have one more pigeon and no more boxes. So if I'm to distribute it in these boxes, I have to place a pigeon in one of the existing boxes, and that guarantees that there will be at least one of the boxes which has more than one pigeon, or at least 2 pigeons. Of course, I can pick all the pigeons and put them in one box, and that still guarantees that I have a box with more than one, but then I try to spread them out to try to have it, but I'm still stuck at the end because I still have one extra pigeon and no more boxes, so I have to put it into one of the existing boxes. So that is the principle we are working with. Now the question here asks that if you have a set containing n positive integers, we need to show that there is a subset such that the sum of the numbers in divisible by n. So this, if you have any n integers, this must work. So I gave an example of the integers do not have to be consecutive, but that it is easier to. So the claim is that if you have 4 integers, you must have a subset in here whose divisible by 4. So here you can see if you pick the subset consisting of just 1 and 3, if you add them, you will get 4, and 4 is divisible by 4. The numbers don't have to be consecutive, but this is just for you to get the point behind the question. So how can you prove this in a general? Are we up to that point?
Yes, we are.
Okay. Yes. So now let's take any set of n positive integers, which we will label as a1, a2, up to an. So we have our n integers. We do the following setup. This setup is you get cumulative sums of the elements in the sequence. So B1 will be the sum of, B2 will be the sum of A1 and A2. If I was to write B3 would be the sum of A1, A2, and A3. So this goes on up to the end, and Bn will be the sum of all the numbers in the set, right? So if with this setup, then I know that all numbers B is strictly less, they are distinct, they can never be equal, because all my integers A1 are positive. So anytime I add some integer to set my collection, I keep increasing it. So this will go all the way up to Bn. So none of these two numbers are equal, right? We have n numbers which are not equal. All of them are different. Now, the claim is that we need to find a subset which is a subset of the original set, which is divisible by n. So we have two cases that arise. One case is where at least some of these numbers, it can happen, some of these numbers, B1, some number out of that set, say, let's call it I, is divisible by n. If that happens, then our work is done. Then the sum of numbers that make a number would be the subset we are looking for. If the number is B2, the subset we'll be looking for is A1 and A2. The sum of A1 and A2 will be divisible by n. At least one of these Bn's is divisible by n. But what if none of them? What if none of these B1 possibilities, none of them, this B1 up to Bn is divisible by n? What happens in such a case? So none of them be but I'll try to. So that means it's always possible to write, say, B1 as some multiple of n plus some non-zero remainder. So let's call the remainder R1. So the same happens, be able to write it as a multiple of n. Maybe now the n. I hope the writing is making sense. Plus some non-zero, to be a zero remainder, because we have made the assumption that none of these b's are divisible by n. So this goes on all the way to the end, up to Bn. It will be posed n as some n, so I call it Kn multiplied by n, plus some non-zero, a total of n numbers here, R1, R2, up to Rn. They are n numbers. But what are the possible values for these numbers? They are non-zero remainders obtained by division by n. Now, the possible remainders when you divide by n would be 0, 1, all the way up to all the possible remainders are actually n. If you start from 0, there will be n possible remainders. But remember, all our remainders are, so these n numbers, this set of n minus 1 numbers, right? If I have n minus 1 numbers, and I want to, out of these minus 1, I want to make a list of n numbers, I have to repeat one of these numbers, right? So I have n numbers. Each of these n numbers is for this set is 1. So I need a list of n numbers made up of numbers from this set. I have to repeat one of these numbers. That's the application of a pigeonhole, right? So best that means there must be at least two that have a remainder, right? Are we together up to that point? So this is
Yes,
still
we
an
are.
explanation of the same thing. So let's label those two numbers BI and BJ. Suppose we know they exist, they must exist. So there must be two that have the same remainder. So let's just pick them as BI and BJ. So then this difference, BJ minus BI, so the assumption here, we assume that I is less than J. So BJ is definitely bigger than BI. So, and this difference will be divisible by N. Why is it divisible by N? Because we made the following assumption. We know that BI will be use AN plus R. They must have the same remainder, right? So I'll just write the remainder as R. And BJ again will be some multiple, let's call it SN, some multiple of N plus some remainder. So if I get the difference, if I subtract BI from BJ, I will end up, so BI minus BJ will give me this S minus A multiplied by N. But what is BJ minus BI, right? BJ minus BI is the sum of all these numbers, right? And it is divisible by N. But what are these numbers? These are numbers, this sum of the numbers from the original set. So what we have actually found is a subset of the original set whose sum is divisible by N. So we have proved that if you have a set of N numbers, it's always possible to find a subset from that set whose sum is divisible by N. We considered the two possible cases, one where at least one of the BI is divisible by N. Check, then the sum we're looking for would just be the sum of the numbers that make up BI. But if none of them is divisible, we apply the Pigeonhole principle that we are guaranteed to have the same remainder. The difference which is out of time. I don't know if we can cover what there.